This video is a continuation of the previous video, where we'll be finishing up code generation for the simple language, dealing with function calls, function definitions, and variable references. So just to remind you what we're working on, here's the simple language. And again, we have a bunch of different kinds of expressions. And we dealt with all of these last time, except for variable references and function calls. And of course, we also have function definitions. So as I said in the introduction, these are the three constructs we'll be looking at in this video. The main issue in designing the code generation for function calls and function definitions is that both of these will depend intimately on the layout of the activation record. So really, code generation for function calls, code generation for function definitions, and the layout of the activation record all need to be designed together. Now, for this particular language, a very simple activation record will be sufficient. Because we're using a stack machine, we're modeling a stack machine in our code generation, the result of a function call will always be in the accumulator, and that means there's no need to store the result of the function call in the activation record. And furthermore, the activation record will hold the actual parameters. So when we go to compute a function call with arguments x1 through xn, we will push those arguments onto the stack. And as it happens, these are the only variables in this language. There are no local or global variables other than the arguments to a function call. And so those are the only variables that will need to be stored in the activation record. Now recall that the stack machine discipline guarantees that the stack pointer is preserved across function calls. So the stack pointer will be exactly the same when we exit from a function call as it was when we entered the function call. And this means we won't need a control link in our activation record. The point of a control link is to help us find the previous activation, and since the stack pointer is preserved, we'll have no trouble finding it when we return from a function call, and we will never need to look at another activation during a function call since there are no non-local variables in the language. We will, however, need the return address, and that will need to be stored somewhere in the activation record. And one more thing, it turns out that a pointer to the current activation will be useful. Now, this is to the current activation, not to the previous activation. And this pointer will live in the register FP, which stands for frame pointer. This is the register name on the MIPS, and the name is chosen to denote the frame pointer, and by convention, compilers put the frame pointer there. What the frame pointer is good for, well, it points to the current frame, so that's what the name comes from, but what it's good for, we'll see in a few minutes. All right, so to summarize, for this language, an activation record that has the caller's frame pointer, the actual parameters, and the return address will be sufficient. So let's consider a call to the function f and has two arguments x and y. Then at the time the call is performed, before we start executing the body of the function, this is what the activation record will look like. So we'll have the old frame pointer. So this is the frame pointer that points to the caller's frame, not to the frame of the function that we're executing. And the reason that it does that is that we have to save it somewhere, because the frame pointer register will be overwritten with the frame pointer for the current activation. And so we have to save the old one so that we can restart the caller when we return to it from the current function. And then there are the arguments of the function, and notice that they're pushed on the stack in reverse order. So the last argument is pushed on first, and the first argument is at the top of the stack. And the reason for doing it this way is that it'll make the indexing to find the arguments a little bit easier, a little bit simpler. And then we have the stack pointer. So there's nothing here. And what will go here is that the callee, the function that we're calling, will push on the return address. So this is where the return address will go. And these elements, the caller's frame pointer, the arguments to the function, and the return address of the called function will make up the activation record of f. Now, a bit of terminology. The calling sequence is the sequence of instructions of both the caller and the callee to set up a function invocation. Okay, so that's referred to in compiler lingo as the calling sequence. And we're going to need a new instruction to show the calling sequence for this for function calls, and that will be the jump and link instruction. So jump and link, what it does is it jumps to the label that's given as an argument, and it saves the address of the next instruction after the jump and link in the register RA, which stands for return address. So what would happen in a jump and link instruction, so if I have jump and link to label L, and then there's, say, an add instruction that comes next. I don't know what it is. It's the address of this instruction, the one after the jump and link, that will be stored in the register RA. So this instruction will jump to L. It will store the address of this add instruction in RA, and it will execute whatever code is at L. And then the code that's at L can execute a jump back to the address in here to execute the return to the caller. So now we're ready to actually generate code for a function call expression. So let's say we have the call f of E1 to En, where of course E1 through En are expressions, and let me change colors here. So these are expressions here, not values. So how are we going to do that? Well, the first thing we're going to do is we're going to start building the activation record. And so we save the current frame pointer. This is the frame pointer for the caller. Okay, so this is pointing to the caller's frame. Okay, and we store that at the stack pointer. We have to bump the stack pointer. And then we generate code for the last argument for En. Right? And so that code gets inserted here. And then we push it on the stack. So we store the result of En, which will be in the accumulator A0 on the stack. And then we bump the stack pointer. Okay, and then we'll do that for all the arguments, finishing up with E1. So we generate code for E1, and we push it onto the stack. Okay, so now all the arguments are on the stack. Okay, and now we just do the jump and link. So we've done as much of the work, and much of the calling sequence as we can do on the caller's side. So this code is executing in the function in the caller. Okay, so this is the caller side of the calling sequence, and it builds up as much of the activation record as it can. In particular, it's evaluating the actual parameters and pushing them onto the stack to form part of the activation record for the called function. And then we do the jump and link, and we jump to the entry point of the function that we're calling. So this is a call to F, and so we jump to F's entry point. So a few more things to note. First of all, as we discussed on the previous slide, when we execute the jump and link instruction, that is going to save the return address in the register RA. And that address will be this address here, the one that comes after the address of the next instruction after the jump and link instruction. And then notice also that the activation record we've built so far is 4 times n plus 4 bytes. So this is where n here is the number of arguments. Each argument takes up 4 bytes, and then 4 bytes for the old frame pointer. Now we're ready to talk about the callee side of the calling sequence, and we're going to need one new instruction for that. The JR instruction stands for jump register, and it just jumps to the address in its register argument. So now the callee side is the code for the function definition. Okay, so this is the code that actually executes the body of the function. And how do we generate code for that? Well, let's take a look. Now, actually, the very first thing that should be here is that this first instruction of the callee side is the entry point. So we're missing the label here. So this would be labeled F entry. Okay, so this is the target of the jump and link instruction. And then the very first thing we do is we set up the frame pointer. So we copy the current value of the stack pointer into the frame pointer. That points to the end of the frame for the callee, for the new function that's being executed. We also save the return address at the current position on the stack. So remember, there was one more thing to do, one thing that was missing on the caller's side of the calling sequence, which is the return address. We don't know the return address until after the jump and link instruction executes. And so the callee is the one that has to save that value. Okay, so after the jump and link, the RA register contains the return address, and then we save it into the frame. All right, and then we push the stack pointer. Okay, and now we just generate code for the body of the function. So now at this point, the activation record is completely set up, and now we can just generate code for the function body. And after the function body executes, of course, the stack pointer will be preserved. And that means that the return address will be at 4 offset from the stack pointer. So we can load the return address back into the return address register. All right, and then we can pop the stack. So here we're going to pop off the current frame from the stack. And that's going to be some size, z, which I haven't shown you what it is yet. But we'll calculate the size of z in just a minute. This is going to be an immediate value, so that's a constant that we plug in there. And then we load the old frame pointer. Okay, so once we've incremented the stack point, we've popped off the existing frame, and so now we're pointing at the frame pointer at the first. We're pointing at the first thing beyond the previous stack frame, and what was that? Well, that was the first thing that we saved in the stack frame for f, and that's the old frame pointer. So now we restore the old frame pointer so that the function that called us will have its frame pointer back, and then now we're ready to return and to resume execution of the calling function. We just do that by a jump register to the return address. All right, so note here that the frame pointer points to the top of the frame, not the bottom of the frame. Okay, so that will actually be important when we talk about how we use the frame pointer when we get to talking about the variable references next. And the callee pops the return address and the actual arguments and the saved value of the frame pointer from the stack. So the callee pops off the entire activation record and also restores the caller's frame pointer. And then what's the value of z? Well, there are n arguments, each of which take up 4 bytes. So the size of the activation record is 4 times n, plus there are 2 other values in the activation record. One is the return address, and the other one is the old frame pointer. Okay, and the space for 2 more words is 8 bytes. So that's the size of the activation record, so that's how much we have to add to the stack pointer to pop the activation record for f off of the stack. Just to give you a sketch of what this looks like before the call, we have the frame pointer for the caller, and we have the current value of the stack pointer. And on entry to the function, okay, after the calling function's side of the calling sequence has completed, what's on the stack? Well, we have the old frame pointer and the 2 arguments, and then the stack pointer points to the next unused location, which is where the return address will go. All right, then we do the jump and link, we jump over, and the return address gets pushed onto the stack, and the frame pointer gets moved to point to the current value of the frame, okay, to point to the top of the frame, okay. And then after the call, what has happened? Well, we've popped everything off the stack. We've popped the entire activation record for the called function off of the stack, and so now notice that we're back in the same state. So again, function calls have to preserve the invariant that the stack is preserved across the call. So the stack should be exactly the same after the call as it was on entry to the call. So we're almost done with code generation for the simple language. The last construct we need to talk about is how we generate code for variable references. Now, the variables of a function, again, are just its arguments, just the parameters to the function. There are no other kinds of variables in this simple language. And these variables are all in the activation record. So really all we have to be able to do is generate code to look up a variable in its appropriate place in the activation record. But there is one problem, and that's that the stack does grow and shrink with intermediate values. So when you call a function and you begin executing its body, values will be popped and pushed onto the stack besides the activation record. So think back to the code generation for plus and minus, and if then else, intermediate values were being pushed and popped from the stack. And so what this means is that these variables that are in the activation record are not at a fixed offset from the stack pointer. So we can't use the stack pointer very easily to decide or to find those variables. So the solution is to use the frame pointer. The frame pointer always points to the return address in the activation record, and because it doesn't move during the execution of the function body, we can always find the variables at the same place relative to the frame pointer. So how do we do that? Well, let's consider the ith argument, x sub I, and this is the ith argument to the function. So where is that going to be relative to the frame pointer? That will be at offset z from the frame pointer, and z is just 4 times I. All right, and this is actually the reason here for pushing the arguments on the stack in reverse order, starting with the last argument to the function, because it just makes this index calculation simple. It wouldn't be that much more complicated if we push the arguments in the other order. It just makes it a little easier to see how the indexing works. And anyway, this index, this offset, is being calculated at compile time. So notice that this number, this 4 times I, is something that the compiler knows. And what we're putting into the code here is just a fixed offset. So we're not actually doing that multiplication at runtime. that z here is just a number that's computed statically by the compiler. So anyway, we just load at offset z, which is the 4 times I, where I is the index, the position of the variable in the list of parameters. At that offset from the frame pointer, that's where xi is stored in the activation record, and we just load it into the accumulator. So that is the entire code generation for a variable reference. Here's a little example. So for the function, the hypothetical function that we've been looking at with 2 parameters x and y, x is going to be at the frame pointer plus 4, and y will be at the frame pointer plus 8.